All right, today in this lecture, we're going to go ahead and review a pretty simple concept that you picked up in either Arrow 300 and or Math 244, which is on solving first and second order ordinary differential equations. And you can look at this in Kreisig or in a number of other math books, but this is pretty fundamental ODE stuff. What we really want to get to is the idea that for all dynamic systems that we can represent as linear ordinary differential equations, we can set them up and solve them in the same way. And so really, if we can solve first and second ordinary differential equations, then we can solve any order ordinary differential equation. And this should serve as a review. So by way of example, let's look at a simple RC circuit. And what I'm going to do is assume that I have some circuit here. It's got a capacitor, say, and a resistor. So I've got a voltage drop across the capacitor, voltage drop across the resistor, and I have some current that's currently flowing through there. And so what that means is that, say, at time t equals t naught, and we'll just say that's 0 seconds for convenience, then VR is equal to VC, which is equal to some initial voltage in the system. So in other words, I've actually already set the system up to have some current in it, and I'm going to see what happens. And so we can go ahead and start to model this, and we can say recall that VR, so the voltage drop across the resistor, is the current times the resistance, and that Vc is the charge in the capacitor divided by the capacitance. We also may recall that the current is the negative of the time rate of change of the charge on the capacitor. So using those two together, create a new page here, we can then say that, all right, so this is using the relationships for voltage and capacitance and resistance, then that IR is equal to Q divided by C. And I can take the derivative of both sides of this whole thing, and I end up with d by dt of the current times the resistance is equal to d by dt of the charge times 1 over the capacitance. And now I can use my current charge relationship, so di dt times R is equal to minus the current times, or just divided by C. Now, how do we solve this? Well, you may recall we used a principle called separation. So we separate and integrate. All right. And when we do that, basically what I do, the idea of separation is I get all of the variables that are alike together. Before we go on, I do want to point out this is a first order ODE, right? So it only has one derivative in time. It's linear because there are no products of current or the derivatives of the current. And it is constant coefficient here, meaning it's autonomous because R and C are constant in this case. So really what I mean by the solution is I want to know what is the time history of the current starting from the initial conditions and then just letting things go. So I'll create a new page here, and we can now look at go ahead and solve this. Well, the separation part means let's take di I, and that's then equal to minus dt over rc. So I just multiplied through by r over dt and multiplied through by dt over r, and then multiplied through by 1 over I. And then I can go ahead and integrate both sides from t naught equals 0 to t, say, and from I naught to I. And this is a pretty simple integral to do. You know, the integral of 1 over I is just the natural log of I evaluated from I naught to I, and that's got to be equal to minus t over rc evaluated from 0 to t. So this is just minus T over RC and minus 0 over RC. So all that goes away. And this is just going to be the natural log of I minus the natural log of I naught. Well, we know that's just the natural log of I over I naught. And that's equal to minus T over RC. Take the exponential of both sides, and I end up with then that I over I naught is equal to the exponential of minus T over RC. And I can then write that I of T is just I naught times the exponential of minus T over RC. So there's our nice little solution. We'll go ahead and create a new page. So we're on page 4. You can also write down, just in case we wanted to see this, that the voltage, right, is just I times R. Well, we just solved for the current. So if I multiply that by R, then what I'm saying is that the voltage is equal to V naught over R times e to the minus t over RC. And we're also going to let RC equal tau. So, and this is referred to as the time constant, and we'll see why in a second, if you don't remember. Sorry, I'm getting used to this pen. Then we now have that I equals I naught e to the minus t over tau, or V is equal to, sorry, no R here, V naught e to the minus t over tau. So both of these functions, whether it's the current or the voltage, are just exponential decays, because notice tau, the way we've defined it, is always positive, because R and C are both positive. We have some initial value for I or V, and then this term here decays away at some exponential rate, which is given by this 1 over tau, so that's why it's referred to as the time constant. So in general, I could plot something like this, say, plot the T there and say the voltage here, and I would start at some initial voltage. Whoops, let's see, that was an accident. Say some initial voltage V naught, and it would just decay away exponentially over time and eventually go to 0. And this tau time constant is going to tell us kind of how fast the thing decays away. It might go like that. Notice we don't have the case, but if tau were negative, then we would have something that would grow exponentially. And if tau were 0, then it would just be a constant. Wouldn't be very interesting. But the take-home message here is that first-order differential equations yield either exponential growth or exponential decay in their solution, and no other solutions are possible. There are plenty of other examples of this: conductive heat transfer, radioactive decay. Those are all examples of first-order differential equations which we can solve in the same way.